Okay, the next set of videos that I'm going to work on are based on examples that are provided in Chapter 4 of Heck et al.'s multi-level modeling of categorical outcomes using IBM SPSS. And the data set was actually downloaded from this website right here. So in Chapter 4, the example concerns multi-level modeling with a categorical outcome variable that is essentially dichotomous. So the first model that I'm going to illustrate in this video is essentially one that incorporates no predictors in it. So essentially it's what's called an unconditional or null model. The data set that you see that's open right here, again, was downloaded from that website. And we have data on a number of students who are nested within their respective schools. So basically, the level 1 unit is students, the level 2 unit is schools. So the level 1 outcome variable is reading proficiency. And so the students were coded either 0 for being non-proficient, 1 for being proficient in reading. Later on, when we start running models that incorporate level 1 predictors, we will be including these variables right here. One variable is low SES, which is coded 0 for not being low in SES, and 1 being identifying a student as being low in SES. Female, which is coded 0 for male and 1 for female. And then minority status, which is coded 0 for non-minority status and 1 for minority status. The level 2 identifier is school code, which you see right here. And then also we have some additional school-related predictors as well, which is a school composition variable, and then sort of a size of the school variable as well. So, like I said, in this video, we're going to basically talk about the unconditional or null model. And what we're going to be looking at is whether there is significant variation across the schools in terms of their levels of reading proficiency. So based on the coding, in conventional, or, when you have an outcome variable that is treated as continuous, as in the case of standard multi-level modeling, the mean for each school on whatever the outcome variable would be is essentially the intercept for the school. And so if we were to run an unconditional model, we'd be predicting variation in the means on the outcome variable. In the context of binary logistic regression, we can compute a mean involving the zeros and ones, but that mean is actually going to reflect a proportion. And so all of the schools themselves will have a proportion of students who would be identifiable as being having reading proficiency or not being reading proficient. So the variation in intercepts is actually variation in proportion of students in the schools who are identified as being reading proficient. So we're going to run the analysis. We're going to go to Analyze, Mixed Models, go to Generalize Linear. Okay, and so if our dependent variable was continuous or being treated as continuous, we would use the linear option. Because we have a dichotomous outcome, or if we were incorporating any other type of categorical outcome, we would want to be sure to use the Generalized Linear Mixed Models option. So we're going to click on this, and you'll notice too that it looks a little different from the other approach using mixed modeling. And what we'll do is we'll put our level 2 identifier over in the subjects box. So we have to drag it over and click that in. Now keep in mind that this is set up already as an ordinal variable in the data set. And so that actually allows us then to move this over to the subjects. If it was nominal or ordinal, we can move it over. If it were a scale variable, though, I don't believe the program would actually allow you to move that identifier over. So you want to make sure that you use the correct scaling and basically set the scale before you try to move it over to the subjects box. Also note that when you're running the mixed models through SPSS, the scaling of your variables that you have in the data set is going to impact the options that you have available through this options. So just kind of keep that in mind. And so, yeah. So at any rate, we'll move on to fixed effects. And so now we'll say use custom target. And the target variable, we're just going to click on this button right here and go down to the reading proficiency variable. So the reading proficiency variable in our data set is being treated as nominal. And by virtue of the variable being nominal, you'll notice that we have the target distribution and relationship link. These options are all highlighted right here. There's also a custom option that's also possible as well, and we're not really going to go into that in this particular video. But you can see that we have multinomial logistic regression, binary logistic regression, binary probit, and so forth. So so at any rate, if this variable right here, let's just say for argument's sake, let's say the variable happened to be a scale variable, you'll see that the target distribution and relationship link now highlights this over here. So make sure that you've correctly specified the scale of your variables because it does impact which distributions and relationship links are going to be highlighted. So I'm going to click on binary logistic regression. So that's essentially what we're going to be running in this demonstration is a binary logistic regression that incorporates no predictors. It's essentially a multi-level version of this. So at this point, I will click on fixed effects, and you'll notice that by default, it's already highlighted include intercept. So in other words, by incorporating the intercept, you'll see up here it says main, it's got intercept, so that's already included. If I didn't have this highlighted, you'd see that it would go away and it would say no intercept. But we want the intercept that's included because the fixed effect is essentially the grand mean of the intercepts, which would be essentially the average proportion of students being reading proficient across the schools. So we do want to incorporate that. The next step is click on random effects, and under this we'll click on add block. So you'll see first of all there's nothing up here, and so we'll click on add block, and you'll see that by default it's set at no intercept, and we want the intercept to randomly vary across the school. So I'm going to click on include intercept and then go down here. So you'll see intercept is highlighted under main. Under subject combination, I'm going to click on school code. And the random effect covariance type, we can just basically leave as a variance component because the only variance component that's going to be estimated is going to be the variance of the intercepts. The other thing to note too in the context of modeling with categorical outcomes is that there will be no level 1 variance term. So unlike standard multi-level modeling with a continuous outcome where you would be estimating the variance at level 1 in terms of the level 1 outcome and the variance in terms of the level 2 intercepts, here we're only going to be estimating the variance of the intercepts. Okay, so now that we've clicked on that, you'll see it says intercept yes, and so now this is telling us that we've correctly specified the model. Under build options, you'll see several possibilities here. You'll see it says sorting order, and where this becomes kind of important is in terms of with our categorical outcome, and in particular with the outcome like this, a nominal variable such as this. We want, we'll have to have reference categories and a target group in order to carry out our comparison. So we're essentially have to determine, which group is a reference category or a baseline category and which one's a target category. So like in this particular case right here, our outcome variable is reading proficiency, and so we would have essentially two groups. One group that is coded 0, which is the non-reading group, reading proficiency group, and then a group that's coded 1, which is the reading proficiency group. And So the sorting order pertains to, really it's addressing the question of which group do you want to be treated as the baseline or reference group, and which one do you want to treat as the target group. If it's set at ascending, what it's going to do is it's going to treat the group that is coded 1 as the baseline group, and the group that's coded 0 as essentially the target group. And that's fine. There's nothing wrong with it. I tend to prefer to assign the group that is coded 0 to the baseline or reference group category, and the group that's coded 1 the target group status. So to do that, I can click on this button and select descending, and that will accomplish that. Where it says sorting order for the categorical predictors, we don't have any predictors in this particular model, but if we did and we incorporated, let's say we incorporated low SES, female, and minority status as predictors, all of these are going to be recognized in the program as being categorical, and they would be treated as categorical predictors, or basically factors. And so if I wanted to utilize sort of the same rationale as I did with the categorical target group, then I could also select ascending or descending. So we're not going to do that in this particular video, but that's just to highlight that particular issue. Like I said, if I had the predictors in the model, I probably, given the coding of 0s and 1s, I probably would want to treat the baseline categories as 0 and the target groups as 1. Additionally, we have tests of mixed effects or fixed effects and coefficients. The default is assuming model assumptions are correct, but I'm going to stay true to the presentation in the chapter and click on use robust estimation to handle violations of model assumptions. So next I will click on run. And you'll notice that the setup is looks kind of like this. There's actually two options available in SPSS. If you go through this in terms of how it's presented, let's see, I'll show you really quickly. If you go under options, if you want the other approach, if you'll go to the output, where it says output display, you can click on pivot tables and charts and click on OK. And then if we run that, run the model in that way, you'll see that it looks a little bit more familiar, more like what we typically get with the normal multi-level model with continuous outcomes. So I'm really kind of less of a fan of this presentation, but this is another option. So at any rate, just kind of scrolling down this output using the second version of our output, you'll see that you get a classification table, overall percent correct. Basically, this is kind of looking at the correspondence between predicted and actual memberships, group memberships on the level 1 outcome variable. Given that there's no predictor variables, really it's just reflecting the overall proportion of students that are kind of falling into the reading proficient group. When we go down to the fixed coefficients, you'll see right here we've got intercept and then the coefficient. Keep in mind that essentially this is, the coefficients in logistic regression are generally reflecting the relationship between predictors and the outcome variable in terms of change in log odds for every 1 unit change on the predictor variable. Since we don't have any predictor variables in the model, this is essentially a log odds associated with falling into the reading the reading proficient group. So it's not exactly in terms that are when you're talking about log odds, it's not exactly intuitive. Oftentimes we can kind of refer to the concept of odds to make a little bit more sense out of things. And basically an odds is just a ratio of probability. So we could say the probability of being in, of group A over the probability of being in group B. So if group A is our target group and group B is our reference category, then the odds is reflecting a ratio of probabilities. And so a value that would be greater than 1 would reflect a greater probability of falling into the group A, which would be the target category. A value less than 1 would reflect a greater probability of falling into group B, and then a value of 1 would basically indicate equal probability of falling into the two groups. So, given that there's no predictors in the model, we can just basically look at this right here as essentially an odds, and we could say essentially the probability of a student being identified as reading proficient is about 2.5 times greater than the probability of being identified as not reading proficient. So scrolling down, we also have our random effects tests and so forth. You'll see down here it says residual effect, estimate 1, and there's no test. And that's what I was saying before, is that there are no level 1 residual variances in the context where you have a categorical outcome variable. So we can't test this for statistical significance. However, we do have down here random effect. This is the variance estimate for the intercepts, and we have essentially a z-test, and it's indicating statistical significance. And so that's telling us that there's significant variation between schools in terms of the proportion of students identified as being reading proficient. So that indicates to us that there might be level 2 predictors that could be added to the model that would help to explain that random variation. And by the same token, we could theoretically add in level 1 predictors that would help to do a better job of predicting membership in the groups. One other thing to note is that really, because you can't have a variance that is less than 0, then technically the significance test, the p-value is for a two-tailed test. So technically the p-value can be treated as half of that's printed out here. It doesn't really make any practical difference because it's already significant at the p less than 0.001 level for essentially a two-tailed test, but in some cases where the significance level is a little bit more borderline, then you can still have the p value and use that to determine statistical significance. So that pretty well covers the first demonstration in this video, and the next video I will begin talking about adding in level 1 fixed predictors.